Welcome to Marvin Test Solutions' presentation on implementing a mmWave device interface for ATE applications. For satellite communications and 5G new radio, beamforming has become a common method for implementing phased array mmWave antennas. Production test solutions are required for testing of packaged mmWave beamforming devices used in these arrays, which presents a significant challenge. Manufacturers require test solutions that can support multi-site, multi-port, high-performance VNA test capabilities. And while multi-port mmWave VNA instrumentation is available from several vendors, the implementation of a production-quality, multi-port DUT tester interface has largely remained unaddressed by the semiconductor test industry. This presentation outlines the design and construction of one such solution, consisting of an integrated test interface and device load board to support testing of multi-port, beamforming mmWave devices operating at frequencies of up to 50 GHz. Some of the challenges associated with supporting mmWave test interfaces include providing a DUT interface that is compatible with wafer probers, device handlers, and manual device insertion. This can be met with innovative mechanical design approaches. But the key to meeting production testing of mmWave devices is providing a test receiver interface that can deliver quality signals, be reliable, and provide consistent, repeatable test results. Guaranteeing reliable and repeatable mmWave measurements requires careful attention to design details and implementation of the RF transmission path from the RF test resources through the tester interface to the load board and terminating at the DUT socket. Specifically, selection of interface cables, connectors, and the load board design parameters are critical to ensure quality and repeatable test results. The receiver interface implementation supports the delivery of 24 VNA RF signals via a 2.92 mm SMK blind mate connectors to a device load board. General-purpose POGO pin blocks provide for digital control signals and DUT power. The transition from the blind mate connectors to the load board is accomplished via semi-rigid cables that connect the SMK mating connectors to through-hole mini SMP RF connectors, which are part of the load board's assembly. Considerable time was spent designing the load board and simulating its performance. The load board construction consists of a 10-layer PCB using Rogers 3003 laminate with stitch signal and ground traces to guarantee uniform trace impedances. Simulation results showed excellent performance up to 50 GHz. The design supports 4 devices, each with 5 RF ports, 1 RF common, and 4 transmit-receive ports. Both manual insertion and automated insertion via an Epson NS8000 series handler are supported for production testing of packaged devices. Ensuring accurate S-parameter measurements requires calibration to a reference plane, ideally located at the device under test. Using time domain gating, an automated fixture removal or AFR method was employed to extract S parameters from an open fixture with the DUT removed from the socket. An initial calibration to the receiver interface was performed using calibration standards. The extracted S parameters from the AFR measurement were then applied to move the measurement reference plane from the receiver interface to the DUT interface. Tests and measurements performed with the system included contact test, IDDQ measurements, SPI digital interface control, and S11, S12, S21, and S22 S-parameter measurements. Intermodulation distortion was also measured, and programmable gain and phase performance was verified against their respective programmed settings. In summary, the described test interface and system was able to test multi-port mmWave production devices at both 28 GHz and 39 GHz. RF performance of the receiver load board interface exhibited excellent S-parameter characteristics over the range of test frequencies, providing repeatable and reliable RF measurement performance. And judicious selection of RF connectors and cables in conjunction with the AFR method provided a high-quality and reliable mmWave interface for ATE systems. Thank you for listening to Marvin Test Solutions' presentation on implementing a mmWave device interface for ATE applications. If you'd like further information, please visit our virtual booth by searching for Marvin Test Solutions in the exhibitors list. Once at our virtual booth, you'll be able to download brochures or even chat with a member of the Marvin Test team. If you'd like to learn even more about Marvin Test, you can search us on the web at marvintest.com.